Welcome again, everyone, and thank you for joining us today for the second part of floating point computation, traps, and pitfalls. If you haven't followed part 1 on Tuesday, don't worry, it's already available on our YouTube channel. I'll share the link with you later on. I'm Lavinia Battaglia, the customer service representative here at BUGSENG, and our speaker is Roberto Bagnara, who is CTO and chief scientist at BUGSENG, other than a very passionate computer science professor at Parma University. Not only, Roberto is also a member of the Misuse working group and of the International Standardization working group of the C programming language. Before we start, please note that you can write all your questions in the Q&A section on the left of the screen. Please do so throughout the entire webinar, so at the end we can read the questions straight away and use that time to reply to as many as we can. All right then, once again, let's turn this over to Roberto.
Okay, thank you very much for the introduction and welcome everybody to this second part of the floating point computation, traps and pitfalls series of webinar. So here is the schedule for today. I will recall very briefly what we did a couple of days ago. Then I will go through some machine and compiler dependent floating point issues. I will then present things that may go seriously wrong in floating point computation. And then after having seen so many problems, I will offer some solutions. So we'll go through absorption and summation errors, which we already mentioned in the first part. I will briefly recall this. Overflows and underflows, cancellation, and also a glimpse of what it looks like to do verification via symbolic model checking. And then I will draw some conclusion. Okay, again, this material has been prepared with my colleagues in BUGSENG at the University of Pisa and at the Polytechnic of Milan, okay? And I have borrowed ideas from several individuals, and you find a list in this slide. So thanks to all of them. Okay, so in the previous webinar, we have covered the IEEE 754 floating point standard. And I think I didn't mention in the previous webinar that IEEE 754 and IEC 6559, which is mentioned in the C and the C++ language standards, are exactly the same thing. So whenever I say IEEE 754, I could equally say IEC 6559, so it's the same thing. Okay, so we have seen the format. One important thing that we discovered is that the standard specifies that arithmetic operations are performed as if they were done on the reals, and the real result is then rounded according to the rounding mode in force at that time. We also started looking at a floating point exception, and we have seen that there are some solutions. We will go deeper into solutions today. So we will have more problems today. So as I said, machine and compiler dependent issues, various kinds of catastrophes, and dealing with standard mathematical libraries. But today we will also have more solution. We will see the case of summation algorithms, computing the average of two numbers where overflow and underflow get in the way, solving quadratic equation as an example of how we can avoid a problem that is called cancellation, and as I said, symbolic model checking to detect floating point anomalies. Okay, so let's start with floating point excess precision. There are some floating point units that provide a large register in order to increase precision. So the first one has been the 8087 and all its successor. This unit has 80-bit registers in a IEEE 754 compatible format. They have 64-bit of mantissa and 15-bit of exponent. Okay, so they are larger than a double precision floating point number in the standard. This feature is no longer seen as a very good idea. So the intention was good. The intention was to compute with a larger precision. However, as we can see now in a second, this may backfire in very important ways. Here is an example. So we have a function which is called positive, which is assumed to be called only with an argument that is strictly positive. So it is not working if it is called with 0. However, in this program, due to the large registers of x87, for example, the positive function may be called with 0.0. Why is this? Because d, when it is tested in the if then else statement, may reside in an 80-bit register, so with extra precision. However, as soon as d is written to memory in order to write it to the activation record of the positive function, when it is written to memory, it is rounded to 64-bit. So if it is a small number, this rounding from 80 to 64 bits can result into 0. And so positive is called in a way that was totally not expected by the programmer. So this, as I said, the problem is that as long as quantities reside into FPU registers, they are kept with 80-bit precision. As soon as they are written to memory, then they are rounded. So, and when are they written to memory? This is influenced by factors that are not predictable at the source code level. Okay, so it depends whether inlining took place or not. Okay, for example, here, if the positive function has been inlined, okay, then maybe the value d is not even written to memory, so truncation does not happen. In turn, inlining is influenced by optimization level, okay, and this writing can occur via register spills. So when the compiler is compiling code, it needs a free register, so it spills one register to memory and then reloads it again. So this is very, very common. And this, as I said, it's completely unpredictable by looking at the source code alone. So at the language level, the only defense is not very appealing, because it amounts to force all intermediate values to memory using the volatile qualifier. So here in this example. So here we force the compiler to write to memory the value before testing it. Some compilers have options to tackle this problem. So for example, in GCC, there is the float store and the excess precision options that allow to obtain the desired effect. So now, one of the ways in which this large register can backfire is because of double rounding. However, double rounding is a general issue. So let us see what it is. It has to do with the rounding mode, which is recommended by the IEEE 754 standard. Round to nearest, ties to even. That's what we have said already in the first part of this series. So the nearest number is chosen, and in case there are two of them, one of them will have an even mantissa and the other will have an odd mantissa, and the one with the even mantissa is chosen. So why the standard does it this way? Because it is statistically more precise. So okay, if you study the errors that the various rounding mode can induce, you will see that the burst performance is round to nearest, and in particular the ties to even variety, because it is biased, so it will favor numbers with an even mantissa, but this bias is much less important than other kind of biases other rounding mode have. For example, bias towards plus infinity, or bias towards away from 0. However, there is a problem with this round to nearest ties to even rounding mode, which is the default and the recommended one. And the point is that when you round a quantity twice in a row to less precise formats, for example, you round a long double to double and then the double to float, you can obtain an incorrect rounding. Whereas if you round in one step from long double to float, you would get the correct rounded value. And this phenomenon is called double rounding. Let me stress this. The C standard mandates that the value representable by float are a subset of those represented by double, which in turn are a subset of those representable by long double. Okay, and this ensures that double rounding is not a problem in round down, round up, or round to zero. Okay, because rounding will get you to the same destination whether you do it in one step or in two steps. So double rounding is an issue of round to nearest ties to even. Let's see an example of this problem. So in this program, I have used a macro, the literal, in order to write a very long floating point constant, literal floating point constant, okay, and optionally sticking a capital F at the end of it, okay. So a floating point literal, if you don't put any suffix, it has double type. If you put an F suffix, it has float type. And if you put an L at the end, it will be a long double constant. Okay, so here we have three variables. One is a double, one and two are floats. Double D, it's initialized with the literal without any suffix. So the assignment is a double is assigned to a double. So there is only one rounding. Why do I say there is only one rounding? Because this literal has too many digits. So as we will see in the next slide, it doesn't fit into a double. So the compiler will round it. Okay. However, we will have just one rounding. The literal is rounding to double, and then we have double assigned to double. Similarly, here, we take the literal by sticking an F suffix at the end of it. So this is a float constant, and we have a float to float assignment. Okay, of course, the compiler will have to round this in order to obtain a float constant. Okay, and FD is another float variable. Here we have double rounding. So first, the literal will be converted to double by the compiler, and then we will have a double to float assignment, and this will be the second rounding. And as you can see from the output, we obtain a result that is wrong. Okay, so the correct value is assigned to F. This is the correct rounding by definition. Okay, so given that in FD we obtain something different, that different thing is wrong. So let's see in detail how this happens. Okay, so let us compute D. We round the literal to double. Okay, so the literal is this in blue, and as you can see, the last two bits are underlined. This is to signify that they are outside the 53 bits of precision. Here we are doing in binary. Okay, so these are bits 54 and 55. However, in double, we only can stick 53 bits. So these two bits here that are underlined, they have to go. So the compiler will have to round this literal. And how will it round it? So the previous double is this one in black. the next double is the one in green, and the next double will be chosen. Why? Because it is nearer. Okay, if you add the 1 in this position, okay, you will have the carry will propagate here by just adding in this 1 in this position. Whereas if you want to go back, you have to subtract 3 from this position. Okay, subtract 1 again, subtract 1 again. So the nearest one is the green one, and this is what will be chosen. Now to compute f, the literal will have to be rounded directly to float. So this is the same bit pattern for the literal. This time we have many more bits that are underlined because many more have to go. So we only have 24 bits of precision in float. So these have to go. And how this is done? The compiler will round in its default mode. It will be round to nearest, tail to even. And it is not difficult to see that the previous floating point will be chosen because it is nearer than the other one. Okay, now let us see double rounding. So to compute FD, first the literal is rounded to double. We already know what is the result because we have seen it at the top of the slide. So we obtain this cyan pattern, okay, which is the same as this one. The literal has been converted to a double. Now this double will have to be converted to float, okay? So this is the previous one, this is the next one, and you can see that this time they are at the same distance. You remove the 1 in this position and you get to the previous float. If you add 1 in this position, you will end up in the second float. Which one will be chosen? The one that is even. So the one that is orange will be chosen. However, this is wrong. The correct solution is here in green. We got this, double rounding, okay? Due to double rounding, we have got the wrong result. Literals is just one way in which the problem can show up. Here is another interesting way, okay? We have two doubles, x0 and delta. We add them directly into Z1. But we do also an alternate computation. Let's say that this was done by the programmer saying, hey, I want to do this addition with more precision. So I will convert x0 and delta to long double. So the addition will be performed in the long double format. Okay. However, the output is this. The Z1 is corrected by definition. Okay. So what we get in Z2 is wrong. And why is it wrong? Because we have double rounding. The long double addition of x0 and delta, it's not a long double. So we will first have a rounding of the real result to long double, and immediately afterwards we will have the long double rounded to double in order to perform the assignment to Z2. So this is double rounding. So let us try to take some useful indication of this double rounding thing. First question, do I have to stick an F suffix to the literal I use to initialize float variables? The short answer is yes. Well, in many cases, it will change nothing, but if you don't want to check carefully that whether it is necessary or not, you just use the F suffix and you know that you will not have a double rounding at that point. Okay, another question. In order to increase precision, is it always a good idea casting to a wider format type in order to use the wider format arithmetics? As we have seen, no. In general, this is not guaranteed to work. So sometimes it may backfire because of double rounding. Oh, time for the first poll. So did you know about double rounding?
Okay, so 70%, no, never heard of it. 19%, I knew it is a potential issue, but no more than that. 25%, yes, but I never noticed the problem myself. And 8%, yes, I have been bitten by it.
Okay, so that's very interesting. Okay, thank you very much. So let's continue. Compiler-induced issues. Well, in theory, all aspects of floating point computation are implementation defined, both in C and in C++. Of course, an implementation is allowed to do better. For example, this is a fragment of C18, but this is also present in previous versions of the standard. It is basically talking about large floating point registers. You see, it says that implementation may employ wide register, but have to take care of to honor the appropriate semantics. In particular, it says that implicit spillover register is not permitted to alter the value. So what does this mean? Does this mean that the compilers we use are not compliant? No, because this is in an example, and example text in the C standard is not normative. So it's an example. You can take it as a suggestion, but it's not normative. So in practice, it is as in theory. So compilers can do just anything. In particular, they can assume associativity properties that do not hold. They can assume also distributivity properties that do not hold. They can treat -0 and +0 as if they were equivalent, whereas they are not, as you know from the previous seminar. Assume that NaNs are not possible, and perform incorrect transformations, such as replacing x + 0 with x, which is not always valid. And similarly, x minus x is not always 0. X minus 0 is not always x. We have seen this in the previous webinar. X times 0 is not always 0, and x divided by y is not always the same thing as x multiplied by the reciprocal of y. So let's take a concrete example. So here we have 4 ways to compute the minimum between two floating point numbers that if the computation was done on the reals, they would be completely equivalent. Okay, let us check 2. So M1, it says if x is the least of the two, take x. And the other says if x is the greater of the two, take y. Okay, well, whereas in IEEE 754, they are not equivalent. You can see it from this table. Okay, you take the possible inputs for x and y +0 and -0, and you would see that you would get different results. And if you take the values none and 1, you will see that you get different results. So M1 is different from M2, different from M3, different from M4. None of those is equivalent to any other. However, compilers will generate code as if the last 3 assignments were replaced by M2, M3, and M4 and assign it to M1. So they will assign, compute the same values as if the definition was the one used for M1. And some will also do so in their default configuration, so without any compiler options. For example, the Intel C compiler does this. And why does this? Because the expression for M1 maps directly into machine instructions in the major Intel architecture. So min SS for single precision and min SD for double precision. Okay, you can play with your favorite compiler. For example, yesterday I played with GCC. So without any option, it does the right thing. So it computes this table. And if you use the option -O fast, then it will do something different from the table and different from what is done by the Intel C compiler. So it's something that is not standard compliant. Let's see another example. So summation of the floating point numbers in an array. So we have seen this program in last webinar. We will see it another time today, just as a reminder. So This is not parallelizable unless you are allowed to reassociate the addition, which is not associative, as we know from the first webinar. So nonetheless, a parallelizing compiler might transform this program we have seen in the previous slide to enable four-way vectorization, even if you don't ask for it, meaning in the default configuration. So this is a transformation. As you can see, with this transformation, a vectorizing compiler can produce, can add four values at a time. And so this goes in parallel with parallelism 4. And then at the end, the remaining values, which will be, of course, no more than 3, will be added. But the result will not be the same in general. Okay, so there is a whole lot of things that compilers do that shouldn't do. So not only they exploit non-existing associative properties of addition, as we have seen, but they also exploit the non-existing distributive property. Why do they do it? They do it for speed because pretending that the operation are distributive will expose more common subexpression. And common subexpression elimination is an important optimization. There is an interesting paper by William Kahan, which we will mention also later, explaining how benchmarks for compiler have influenced in a bad way the optimization that compilers do with or without your explicit constant. So here we see another time in this series of webinars, we have seen this very often, that it is crucial to test your compiler. Okay, so let's continue with a taxonomy of things that may go wrong. So, numeric to none. So you have an algorithm, and this algorithm produces a not a number. Okay. Why this is normally a problem? Very few programs have been designed with NaN generation in mind. So as soon as you unwillingly generate a NaN, with this will completely break your program. That's very likely. So NaN will sometimes, in the end, maybe you have an actuator to control, and you do a NaN to integer conversion, which is undefined behavior. Okay. Similarly, many algorithms have not been designed to take into account the possibility of infinite numbers, which are present in IEEE 754. So again, this is very dangerous. A conversion from infinite to an integer is undefined behavior, and the emergence of the infinity can spoil completely your algorithm. So we call this a finite to infinite anomaly. So starting from finite inputs, an infinite number was generated. Another problem very few people is aware of is called ill-conditioned argument. So it's when you call a trigonometric function like sin, cos, or tan with a value that is too large. Why is this a problem? The problem is that as the floating point are dense near, dense not in the mathematical point of view, so there are more floating point numbers near 0. As soon as you go away from 0, you have less and less floating point numbers. And in single precision, for example, when you have a value that is 2 to the power of 23, so what is this, 8 million? Well, you just have 3 floats, 3 floating point numbers or less in a cycle of the trigonometric function. So even though the range reduction algorithms are very precise, calling sin, sine, cosine, or the tangent function on a large number is very similar to call a random number generator. So the result is totally non-significant. because the approximation on the input to those functions is so high that the result is meaningless. Let's talk about underflows. We have mentioned in the first webinar 2 days ago that we have an underflow when a very small quantity is approximated by 0. We now explore a more refined classification. We talk about gradual underflow when we have an operation whose inputs are normal numbers and the result is subnormal number. As we have said already 2 days ago, the emergence of subnormal numbers is something you want to be careful about, because subnormals can be 2 orders of magnitude less efficient than normal numbers. So you can see your application going 100 times slower because subnormals have been generated that you don't know. Okay, and hard underflow is when you have normalized numbers that due to the operation, they result into a 0. Okay, whereas the result computed on the reals is not 0. So we have a relative error of 100%. And soft underflow, we have an operation with at least one subnormal operand, which results into 0, whereas the real result is non-zero. The relative error is still 100%, but this operation may not be the root cause of the problem. So the problem might be that the subnormal should have never been generated. Okay, so you should first look at hard underflow and gradual underflow, and only later take care of soft underflows. So another generally bad thing is called absorption. So I'm just recalling it because it was one of the subjects of the first webinar. It's when we have that one operand is absorbed into the other. So for example, in addition, it is when we do y plus z and we obtain y, but z is not 0. So z was absorbed into y. Okay, and similarly, we can have absorption for subtraction or for multiplication. So let's look at absorption for multiplication. We have that y times z results in plus y or minus y, but z is neither plus 1 nor minus 1. So z has been absorbed into y. Okay, and similarly for division. Now, this is new. We didn't see this in the previous webinar. Cancellation. Cancellation is a very, very important problem. So it's when you do an addition or a subtraction between two numbers, and there is a difference between the maximum of the exponent of the operands and the exponent of the result. So d is the maximum between the exponent of y and the exponent of z minus the exponent of x, which is the result. In this case, we have cancellation. So if d is greater than 0, it means that we have lost digits of significance. So in the input, say we had, I don't know, 13 bits of precision. The output may be 3 bits of precision. So we have got a very important loss of precision. What is the cause of the problem? So since subtractions that are subject to cancellation, they regard numbers that are close to one another, the result of the subtraction is quite often precise. So where does the problem comes from? So if you do a little bit of math, you see that cancellation amplifies pre-existing errors. So let's suppose that y, the value that you have in your quantity, floating point quantity y, is the real value subject to this delta y error. And similarly, z is the real value subject to this error. The question now is, what is the error, the relative error on x if I do the subtraction y minus z Well, if you do a little bit of rearrangement, you find that the relative error on X is this thing divided by the real value of Y minus the real value of Z. And if this is very close, this is a division by a very small number. So it will amplify greatly the errors you have on the operands. And cancellation is a very frequent cause of algorithmic instability. So more often, very often, when you are looking for a cause, the cause of your program not behaving the way you expect, cancellation is the first thing to look at. So look at all the addition and subtraction and ask yourself the question, is it possible here that this subtraction will be subject to cancellation? Of course, subtraction and addition are subject to the same problem. You just change the sign and you turn one into the other. So let us make an example. Let us take a very simple expression, x divided by the difference of x and y. So it's not even a line of code. It's a few characters of code. Well, in this tiny expression, there is an incredible number of things that may go wrong. So in the subtraction, we may have a finite to minus infinity transition. We have two finite numbers here, okay? And their subtraction will give minus infinity. We can also have finite to positive infinity. These are two numbers that when they are subtracted, they will give rise to positive infinity. So the numeric to not a number transition is not possible in the in this subtraction. This is good. We can have gradual underflow. So here we have two normalized numbers. When you subtract them, you obtain a subnormal. We can have cancellation of any number of digits. So any number of digits can be cancelled. So it's trivial to find examples of this. And we can have absorption. Okay, so here it's a case of absorption in which the difference is equal to x. And what can go wrong in the division? Again, here we may have, in this division, you see, we have seen what may go wrong in the subtraction. In the division, we can have a finite to minus infinity transition, finite to positive infinity, numeric to none. This is easy. So, okay, for example, if we enter here with x and y equals 0, so this will be 0. 0 divided by 0, it's a none. We can have an underflow, so normalized numbers, the result is 0. We may have a soft underflow, so the generation of subnormals. Soft underflow. One of the input is already a subnormal, and the result is 0, whereas the result on the reals is not 0. And gradual underflow, so two normalized numbers, and when we do the division here, we end up with the generation of a subnormal number. And we have absorption, so in the division. So in this tiny piece of code, many things can get wrong. So let us go to the issue with standard mathematical libraries. So C and C++ offer a floating point mathematical library. They contain functions such that exponentiation, natural logarithm, sine, cosine, the hyperbolic function, and so on. What is the problem? Is that they come with very little guarantees on the computed result. So, for example, if you go to the GNU libc documentation, even the very latest version, you will see a table of the maximum errors. However, it is explained in the caption that the table lists the maximum error that was observed. So it's just a ballpark figure. So it's really not something you can count on. And in the embedded system world, the situation is not better. So we checked the documentation of all major toolchain providers. Some of them explicitly say in the documentation there is no guarantee. For example, the analog devices compiler for the Blackfin says that, Green Hills says that, Fujitsu soft-tune compilers say that, Texas Instrument and so on. But the majority of compiler vendors leave the lack of guarantees implicit, so basically they say nothing. So we have checked basically all of them. Okay, so why is this important? This is an example. You are not supposed to read it. You have supposed, I show it to you because it contains a lot of calls to the mathematical libraries, and these are highlighted in red. This is a piece of code which is critical. It is part of code to control drones. And this is a piece of code that reads a GPS position and tells the drone what is its position in the world. Okay, so you see that there are many possibilities here for things to go wrong. For example, the logarithm of a negative number. Can this ever become negative? It's important to know this because logarithm of a negative number will be a NaN, and if a NaN is generated here, it will mess up anything. Okay, so there are many. This is another part of the same code. Many invocations to the mathematical library. Okay, the question are: can infinities and NaNs be generated in this code? Can sine, cosine, and tangent be invoked on ill-conditioned arguments? If these anomalies can happen, what are the inputs that may cause this problem? So these are the questions to be answered when you look at a piece of code like that. So we will see a possible solution later. So now it's time for the second poll. So do you use a mathematical library? So do you use these functions? And secondary thing, do you use a library that gives you some guarantees?
Okay, so 28% yes, and the guarantees it provides are okay for my applications. 26% yes, but I'm not sure about the guarantees, if any. 31%, well, they're changing the percentage right now, but I'll keep on reading it. Yes, but it does not provide any guarantees. And 25% no, I do not use any mathematical libraries.
Okay, this is very interesting, especially in the part of people who uses libraries that provide enough guarantees for the application. Okay, so we have seen so many problems. We have been overwhelmed by problems. So let's see some solution at last. So one is just a reminder. We have seen it in the first webinar. I will repeat it here very briefly. So we have to sum several numbers, and the problem is one of the problems is absorption. So here we have the Naif program that sums the numbers in a way that large numbers are summed together first. Okay, so addition is not associative, so the result will change. And in this case, what happens that if we add first the large numbers, then we encounter the small numbers later. The small numbers will be absorbed into the running sum that will be large when we encounter them. So this is the correctly rounded result in single precision. The Naif algorithm only gives me 4 decimal digits of precision. So the first 4 digits are fine, the others are not. So an improvement can already be obtained by reversing the order of addition, so that we first add the small things together, so we reduce the chance of absorption, and then we add the large things later. So by simply this trick, we increase the number of correct digits we get from 4 to 6. However, there is much better for summation, and this is called Kahan summation algorithm. Okay, so again, you can look it up on Google. You will find everything about it. So it, of course, comes with a cost. So instead of just one addition operation, it requires one addition and 3 subtractions. So it's more expensive from the computational point of view. However, the performance in terms of precision is spectacular. In this particular example, we obtain the precise result, so all the digits are correct, and without even reordering the summation. Okay, this was for absorption. Now let's talk about the generation of overflows and underflows. So let's say we want to compute the average of 2 numbers. So on the reals, it is trivial. We add them up and we divide by 2. However, in floating point is not so easy because, for example, if you add them up in floating points, you may get an infinity. And then when you divide the infinity by 2, it still remains an infinity. So it doesn't work. So we have to give a specification for the algorithm that we want. So ideally, we would want to have all these properties. We want an algorithm. These are due to disturbance, by the way. So we want an algorithm that does not overflow, that it does not underflow unnecessarily, such that the result is approximately equal, possibly correctly rounded, but okay, we are willing to give up some precision to the real result. We want the average to be between the minimum and the maximum, of course. We want the average to be symmetric, and we want that the average of the opposites is the opposite of the average. And also we want the approximation not to change the sign. So if the average computed in the reals is positive, we want the average computed on floats to be positive as well. We don't want a change of sign as part of the approximation. Okay, so let's see a few possibilities. So first we have the naive algorithm. So we take the specification x plus y divided by 2, and we translate it into a floating point program. This is quite accurate. It is actually as accurate as possible because division by 2 in floating point, in the binary floating point format, is a very precise operation. The problem is that it may overflow. So when x and y have the same sign, the addition may give rise to an overflow. We may end up with infinity, and infinity divided by 2 is infinity. Okay, so next algorithm is also quite accurate. It says you divide x by 2, then you add the result to the division of y by 2. This is also correctly rounded, assuming that x and y are not too small, because if they are small, you can even have underflow because you do the division before the addition. So you may have underflow, but this is accurate when underflow does not occur and when x and y are not too small. There is another possibility. This is slightly less accurate than the first two. It may overflow, but only when x and y have different signs. So remember that the first algorithm may overflow when x and y have the same sign, whereas this one, may overflow when x and y have different signs. Moreover, this violates symmetry. So it's no longer the case that you get the same result if you swap x and y. You can combine two of these ideas. So in this way, so if the arguments have not the same sign, then you know that an overflow cannot happen. So you can use the first algorithm that is accurate. And if this is not the case, then you use the third algorithm that is slightly less accurate, and by checking the relative magnitude of x and y in absolute value, you re-establish symmetry. Okay, but you can do better. So this algorithm, which is due to Sylvie Bouldeau, computes always the correctly rounded result. So here is the version of the algorithm for float, and this is the version of double. This C constant is in a way a magic number, and these two versions are optimal. So optimal meaning they satisfy all properties and are correctly rounded. So symmetric, correctly rounded, no overflow, no underflow, none of the problems. And the fact that these constants are so large ensures that as much as possible we end up in the else branch. And when we end up in the else branch, we only have 1, 2, 3 floating point operations instead of 4. So these algorithms are also efficient. Okay, cancellation. Let's consider the quadratic equation that everybody knows. So we all know the classical formulas for solution. In general, this has up to 2 solutions in the reals. Okay, it's unstable because of cancellation. When it is unstable, when we have that b square is much larger than for AC. Okay, so in this case, we might have cancellation. If b is less than 0, and then we have that minus b will be almost equal to b squared minus 4ac, so we will have cancellation here. Okay, we have a negative minus a positive, and they may cancel. And similarly, if b is greater than or equal to 0 and b is very near to the square root of b squared minus 4ac, we have a symmetric cancellation for x1. Okay. Okay, then can we avoid cancellation? Well, if we rearrange, if we do some basic computation on the reals, we discover that x2 and x1 determine each other. Okay, so x2 is c divided by ax1, and symmetrically x1 is c divided by ax2. So what is the nice algorithm? Is to compute either x2 or x1, and then compute the other using these formulas. So we compute the one which doesn't give you the risk of cancellation, and then we compute the other. So let's try if this works. So suppose the equation to be solved is this one. Okay. So in IEEE 754 single precision, the correctly rounded result is that we have 2 roots. x1 is this, and x2 is this. Okay. In if we use the naive algorithm, we have cancellation, and you see that for x1, no digit is correct. So all the digits are wrong. Whereas if we do the trick that I have just outlined, so we compute x2, which is not subject to cancellation, and then we compute x1 starting from x2, the result is much better. In this particular case, it is actually correctly rounded. Okay. Now let's do the final thing about verification via symbolic model checking. So What's the problem? Is that the functions in the mathematical library, as I said, normally come without any specification. So, and if you don't have a specification, then it's very difficult. You can formally verify anything. So we at BUGSENG, in cooperation with the University of Parma and Pisa and the Polytechnic University of Milan, we have developed a technology that allows to cope with this situation. Okay, so even though we don't have a proper specification for the function, sometimes we have a partial specification, and sometimes we are able to extract a partial specification from the implementation of the library. And without, even this is impossible, we can still detect many flaws in the program and facilitate its partial verification with testing. So let us take again the program I showed you before. This is the portion of a drone controlling software with many floating point operation, arithmetic operation, and many invocations to the mathematical library. So for this program, our Claire analyzer, at the first run, it found several problems. In particular, it found ill-conditioned trigonometric function arguments. So, for example, in line 19, let us go. So, okay. In line 19, the tangent function was invoked with a very large value for the argument. So the result was completely unreliable. And similarly in other lines. Okay. The checker also found numeric to none transitions. So one is the transition that I have drawn your attention to before. Still in line 19, there is a call to the logarithm function. So this the argument of passed to the logarithm may be negative, and this is what gives us not a number being generated. There is another numeric to none transition. Okay, now the program, you can find it on the internet. It's called Paparazzi, so it's open source software you can find. So there is no documentation about what are the allowed input values, and in particular there are no assertions. So however, even though no check is done in the program, we have added assertions at the beginning of the function. So imposing that phi is between minus half pi to plus half pi, and that lambda is between pi and pi, because these are latitude and longitude. So this fixes most of the issues, but still Eclair finds a numeric to none transition at this line 19 I showed you before. For this, and Eclair gives an example, and this is the example that is triggering this numeric to none transition. So it's a very corner case, because this point here is 10 centimeters from the South Pole. So if the drone was flying over the South Pole, so this might be, this might happen. However, if you inspect the code, you see that there is no check being done on the GPS input channel. So this does not only happen if you go over the South Pole or the North Pole, the code is symmetric, but also if there is a communication problem with the GPS. Okay, so if we strengthen now the assertion to ensure that you never fly over the poles, okay, then Eclair finds no more anomalies and there are no timeouts. So it means that if the model we have on the library, we have extracted from the library is correct, none of the 154 potential runtime anomalies in that piece of code I've shown you can occur. For example, there are no division by zero, there are no integer overflows, no inexact conversion. All of those, Okay, the numeric to none transitions that are theoretically possible in those codes are 66, but though all of those can be excluded. So time to conclude. I am a bit late. So the use of floating point computation for the implementation of critical system is perceived as increasingly acceptable. And even in modern avionics, floating point arithmetic is increasingly used instead of fixed point arithmetic. In this couple of webinars, I hope to have illustrated that there are two key aspects to be considered. First is algorithm selection. So even for trivial things, summing numbers, computing the average, okay, solving quadratic equation, there is the wrong algorithm and the good algorithm, and you better choose the good algorithm. And then program verification. For program verification, there are three main goals. Okay, first is ensure absence of undefined or undesirable behavior. So these are the things, the anomalies we have discussed today. So generation of infinities that are not wanted, NaNs, overflows in conversion to integer, and so on. We want to identify sources of round-off errors, in particular cancellation. Okay, and then we will have the task of proving that the program implements a certain numerical computation up to some specified error bounds. So this is really tricky, and it connects to what I said before. So careful algorithm selection. There are handbooks that help you in selecting the correct algorithm. So I hope that these two seminars have been useful to you, to introducing you to the main issues and what can be done about them. Now, if you have questions, I will be happy to answer them.
Thank you, Roberto. First question. Most microcontrollers nowadays have an inbuilt hardware for mathematical functions. So how the compiler takes care of using the right instructions and register to make sure that these calculations are done in the right manner?
So let's differentiate the two things. So first, hardware bugs. Historically, there have been and still there are bugs in the hardware. So model checking techniques for verifying hardware have seen significant advantages. So in modern hardware, there are less bugs that you can expect. When there are, the compiler writer usually provides their compilers with mitigation action. You will have seen in compilers used in the embedded systems that there are options sometimes to mitigate some known defects of the hardware. Then, of course, the compiler writer must be aware of the hardware they generate code for. However, the point, as I have shown in this webinar, is that really all the aspects related to floating point computation are implementation defined in the standard. And as I've shown, the many compilers will do optimizations that do not preserve the result. So several of them, not all of them, unfortunately, provide options that might be disabled by default. So you better check that allow you to prevent this unsound optimization. Okay, so many compilers have them. And you should, if you want to make sure that your program behaves as prescripted by IEEE 754, you better use them. These options, as I said, are used to increase efficiency. So in some cases, they enable parallelism. So it's a trade-off. The point is that if you use these options, your code will be much faster. But the problem is that it will be unpredictable. So, and this, at least in critical systems, is unacceptable. You cannot accept that your code is unpredictable. You change one option, you enable one optimization, and the behavior changes completely.
Okay, thank you, Roberto. Second question, is there any organization which can certify a particular C compiler for proper functioning of it for mathematical operations?
Okay, no, the compilers cannot be certified. They can be qualified. We had a seminar on compiler qualification. You may want to check it on our BUGSENG YouTube channel. So you can test it. So there are qualification, there are validation suites for C compilers. For example, a very good one is a super test by a Dutch company called SolidSense that has an entire section devoted to IEC 6559, so the standard C and C++ mathematical library. And so this is the only thing that you should do. So you should do two things. You should qualify your compiler, validate it, and the selection of options is crucial in this sense. As I said, sometimes the default of the compiler is not to produce code that is sound with respect to the standard. So you may have to do something in order to add options in order to make sure that the generated code is compliant to the standard.
Next question, and I think last one for now. How can we check the compiler is faithful to my source code?
Okay, so there are two possibilities, one of which is not very appealing. So you check the produced machine code, very expensive, of course. And the other is what I just said. So you validate your compiler. You run the compiler through a possibly very large validation suite, and you check that the results are the one expected. So some of the examples I have given in this webinar, you can use them. So if you are curious, for example, the small program computing the minimum of two floating point numbers in 4 different ways, you can check if your compiler is doing the right thing or not. It will be instructive.
All right, thank you, Roberto, and thank you again, everybody, for joining us today. Of course, if you have more questions, you can always drop us an email at info@bugsend.com. Also, if you'd like to see this webinar again or share it with your colleague, head over to our YouTube channel. We will send you the link in the post-webinar mailing as well. In general, there you will find all previous and future webinars. Let me just quickly remind you that next webinar will be Misuse C++, a subset of C++ for the development of high integrity systems. It's going to be on May 14th, so Thursday next week. Don't miss out because it was prepared with Chris Stapp, who is nonetheless the chairman of the Misuse C++ working group, so big time. Right, we're signing off now. Thanks again, everybody. See you next time.
Bye-bye.